Hello, Calculus 3. Today we're totally changing topics and we're moving on to our integration chapter, chapter 5. And kind of like we talked about, each chapter kind of ramps up and each chapter kind of starts easy. So this is going to be a nice break from the last section, which was kind of the hardest section of chapter 4. Now we get to do the easiest section of chapter 5. So let's begin. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. So today we're talking about double integrals. And double integrals will give us volume of any sort of strange terrain over the xy plane. So in this case, we've got this pretty picture that I stole from your textbook. And today we're only going to do rectangular regions. So if you look at the region R right there, oh dear. So if you look at the region R right here, it is a rectangle. And that keeps things simple. We will deal with the case when it's not rectangles next time. So today we're just doing nice little rectangles. So if you imagine this function right here, if you were to pick a point for each little square, then you would have this grid where you have like x, I, y is there, and then you pick like some point. You might want to pick like the center point, the very far upper left, upper right, whatever you want to do. And then you find the height of these little towers to be whatever your representative point is. You plug that into the function, and then you can kind of add up all these little skyscrapers, and that'll give you an approximation of the volume of this shape. And as you get those skyscrapers to be narrower and narrower, having a smaller base, then you'll get a closer and closer approximation to the actual volume, which is what we get right here. The double integral of the function over the rectangular region R is defined as double integral over your region R. And then notice I'm going to use the phrase dA when I'm using just double integral. And it's a double limit of m and n both going to infinity of a double sum of f of xi, xj, and then this delta a means like this each the area of these little squares is delta a. Now, that might look like something scary to you, but I have good news for you. So there's also such a thing as an iterated integral. And an iterated integral is when we're doing a to b. We do just two integrals here with this. And what it means is that we're basically just doing normal integrals, just doing it twice. So we always do the inside integral first. Once we integrate that, then we do the outside integral. And here is where your dy's and dx's really matter, because here in this inside integral, I've got dy, so I'm integrating with respect to y. Whereas in this integrated integral here, I've got dx, so I integrate with respect to x first. Okay, and then we have this great theorem from Fubini, which says that the double integral here is equal to, if R is a rectangle, and then this is crucial, if R is a rectangle, then the double integral can be written either way. You can do dy on the inside or dx on the inside. And so either way, you're either kind of, if you're doing the inside one first, you can be finding the area kind of going one way or the area going the other way. But then once you found all those areas, you add them all up by doing the outside integral, and you have the volume. And so that's what Fubini showed, is that when you've got a rectangular region, it doesn't matter what order you do this in. So all this means is that instead of doing any limits or anything like that in this section, we're just skipping right to just doing iterated integrals. So here's an example. So if I do this right here, it's not going to matter. So I'm going to do it 2 times. I'm going to do it so x's are from, let's do x's on the inside on the left and y's on the inside on the right. So x's on the inside would be x's go from 0 to 2, y's go from 1 to 2. And you've got x, y minus 3x y squared. X is on the inside, y is on the outside. I could also do it 0 to 2, 1 to 2, and xy minus 3x y squared. Y is on the inside, x is on the outside. So in this situation, I'm going to do the inside integral first. And so then I get integrating with respect to x. I get a 1/2 x squared y minus 3/2 x squared y squared from 0 to 2. So then I've got plugging in 0 will just give me zeros. So then I've got 1/2 times 4 is 2y, and then 3/2 times 4 is minus 6y squared dy. So I took the derivative of I took the integral of the inside with respect to x. Now I'm going to take the integral of the outside with respect to y. And so then there should be no more x's once I've completed this integral. And so then now I do this integral, and I get y squared minus 2y cubed from 1 to 2. And that's going to be plugging in 2, I get 4 minus 2 times 8 is 16, minus plugging in 1 is 1 minus 2. Okay, so that's negative 12 minus a negative 1 should be plus 1, so that's negative 11. Okay, let's try it the other way. Then if I do the integral with respect to y on the inside, then I get outside stays the same. I get 1/2 xy squared minus xy cubed from 1 to 2 dx. That's the integral from 0 to 2 of plugging in 2 for y gives me 2 squared times 1/2 is 2x minus 8x minus plugging in 1 gives me 1/2 x minus x. So in this parentheses, I plugged in the 2. This parentheses, I plugged in the 1. Let's just do that, move the negative through. And then that's equal to 0 to 2 of negative 6x plus 1/2 x dx. So that's integral from 0 to 2 of negative 11 over 2 x dx. Well, integrating there, I get negative 11 over 4 x squared from 0 to 2. And then plugging in 0 gives me nothing. Plugging in 2 gives me a 4, which gives me negative 11. So both cases, I get the same answer. Okay, so let's do another example. So here, I've got the double integral of e to the y cosine x, from where x is from 0 to pi over 2, y is 0 to 1. So again, I'm going to do it both ways. So here, I'm going to do e to the y cosine x, and I'm going to do x first, dx dy. So x is on the inside. X goes from 0 to pi over 2. Y goes from 0 to 1. Over here, I'm going to do integral from 0 to pi over 2, integral 0 to 1, e to the y cosine x. I'm going to do y on the inside and x on the outside. So integrating with respect to x on the inside gives me, well, the integral of cosine x would be negative sine x, and then the e to the y is just a constant. I'm treating it like a constant. So, so then you would get a negative e to the y sine of x. X is going from 0 to pi over 2. I've got dy still on the outside. Plugging in 0 for x will give me 0, so I only really need to plug in the pi over 2. Wait, it's not negative because the derivative of sine is cosine, so it's positive. All right, so then plugging in the 0 is still 0. Plugging in the pi over 2 will give me 1. So this is equal to the integral from 0 to 1 of e to the y dy. And that's a very easy integral. That stays the same from 0 to 1. So that equals e to the 1 minus e to the 0, otherwise known as e minus 1. Okay, let's do it the other direction, or the other way. So we'll do 0 to pi over 2. We'll integrate with respect to y. So integrating with respect to y, the cosine x I treat like a constant, so it just hangs out. And so I've got, and then integral of e to the y is still just e to the y. So e to the y cosine x from 0 to 1, and I still got the dx on the outside. That's integral from 0 to pi over 2 of e to the 1 cosine x minus e to the 0 cosine x dx, and then integrate with respect to x. So then you get e to the 1 is just e times sine of x minus e to 0 is just 1, so minus integrating that one is also sine of x from 0 to pi over 2. And so plugging in 0, you get 0 in both terms. Plugging in pi over 2, you get 1. So it equals e minus 1. Okay. Now, sometimes the order of one way is much easier than the order of another way. So in this case, I've got the double integral of x times sine of xy. And my region is x is from 0 to 3, y is from 0 to 2. Then, let's set them both up, and I'll talk about the hard one, and then I'll do the easy one. So setting them both up, x is from, so I'll do x on the outside over here, 0 to 3, 0 to 2, x sine of xy dy dx. And then I'll do y on the outside, 0 to 2, 0 to 3, x sine of xy dx dy. Okay, now if I wanted to integrate with respect to x here, what would I have to do? Well, I've got multiplication going on. And remember that integrals are the opposite of the derivative, so I need to do kind of the opposite of the product rule. That's otherwise known as integration by parts. So you'd have to set up something like u equals x, and du equals 1, and dv equals blah, blah, blah. Or let's look at the other way before we do anything. The other way, if I integrate with respect to y, then I'm going to do a u substitution. So if u equals xy, then du equals x dy. Makes sense? So then look at that, how that matches that. So this is equal to the integral from 0 to 3. Integral, I'm not going to put in the numbers yet, of sine of u du dx. Now, we could put up these guys, the stars, and put it in later. Or, why not put it in now? No, let's just plug it in later, because then I'm technically not integrating a rectangle anymore. So it might be confusing to some of you. So we'll just equal 0 to 3. Integral of sine is negative cosine of u from stuff to stuff dx. Let's plug in what u is. So then that is negative cosine of u is xy, and y goes from 0 to 2 dx. So that's 0 to 3 of cosine, plugging in. Now I'm dealing with y's. So negative cosine of 2x minus negative, so plus cosine of 0, because 0 times x will just be 0 dx, and cosine of 0 is just 1. Okay, then I'm just going to keep going over here because that's too ridiculous. I'm not going to do it that way. So I'm going to rewrite it. Integral from 0 to 3. Let's rewrite that integral. 0 to 3 of 1 minus cosine 2x dx. And then let's integrate there. So integral of 1 with regard to x is just x, minus integral of cosine 2x becomes plus 1/2 sine of 2x. Right, because the derivative of this should be that. Actually, no, I don't change the sign this time. It's just x stays as minus. X minus 1/2 sine of 2x. And a good double check is to take the derivative of this and see if you get back to where you started. So the derivative of this, I would do the chain rule. The 2 times 1/2 would just give me 1. Yep. So then x is going from 0 to 3. And so then that gives me 3 minus 1/2 sine of 6. And then plugging in 0 is 0. Plugging in 0 to sine is 0. So I'm done. And I didn't have to do integration by parts because I chose to do it the easy way. Okay, so sometimes doing the integrals, the iterated integrals, it basically doesn't matter. Each way is about the same. Sometimes one way will be significantly easier than the other. There are even going to be some situations later on where one way is impossible. So just be aware of that. Okay, now let's find the volume of a solid bounded by the elliptic paraboloid 2x squared plus that's a typo. There's no 2 there. Plus y squared plus z equals 27. The planes x equals 3 and y equals 3 in the 3 coordinate planes. Well, then what I'm doing, finding the volume, so I'm doing a double integral, and it's over the 3 coordinate planes. So my double integral just like how your single integral was always finding the area over the coordinate axis. If you're over the coordinate plane, then you're just doing a straight up double integral, nothing fancy. X equals 3, so the coordinate planes are when x is 0, so then you go x is going 0 to 3. Let's do x is on the outside, y is on the inside. So, and then we have 2x squared plus y squared. No. So this shape, solve for z. Z equals 27 minus 2x squared minus y squared. So that gives us the height of the solid. So then we're integrating 0 to 3 of 27 minus 2x squared minus y squared. D, it doesn't really matter, they're both 0 to 3. So let's do x first and then y. Well, integrating with respect to x gives me 27x minus 2/3 x cubed minus xy squared from 0 to 3. Y, that's equal to 0 to 3 of, well, 27 times 3 is 81 minus 2/3 times 27 would be really like 2 times 9, which would be 18. And then minus 3y squared dy. Let's simplify that. 0 to 3. 81 minus 18. 81 minus 20 would be 61. So 63 minus 3y squared dy. Well, let's integrate there. So that gives me 63y minus y cubed from 0 to 3. So that gives me 63 times 3 minus 27. So then if I pull out the handy dandy calculator and compute 63 times 3 minus 27, I'm left with 162. That is the volume of that solid. Okay, now our last thing is average value. So in calculus 1, or maybe we did this in beginning of calculus 2, whichever. It was either like the end of calc 1 or the beginning of calc 2, we covered average value. So if your function's kind of doing something crazy, you can find the average value by finding the area under the curve. And then if you divide by, if you think about like the square or rectangle that like have the same base as that and the same area, then the height of that rectangle gives you kind of the average value of the function. So in a similar way, if your function is now like doing stuff in 3 dimensions, then you find the volume, and then divide by the area of the base, and that gives you kind of an average value of the top. That's a poorly drawn picture. But so anyway, going back to our integral of x sine of xy, that was 3 minus 1/2 sine of 6. So this is the same situation. So we just, this thing here was, in our situation, was 3 minus 1/2 sine of 6. So to find the average value, just divide by the area of the base. So the base was, x goes from 0 to 3, y goes from 0 to 2. So then if you just take 1/6 times 3 minus 1/2 sine of 6, you get 1/2 minus 1/12 times sine of 6. And that gives you the average value over that region. Okay. So that is it for this section.